He's gonna drink over Mercury. No, this is Archimedes. Okay. He was a Greek mathematician, physicist, and engineer back at a time when that was all the same thing. So it's actually not that impressive. He didn't even have a double major. Okay. So because this was like 287 BC, so he just like if you weren't like smashing rocks with other rocks, you were a scientist. And but he was actually one of the greatest scientists in antiquity. He was one of the first people to calculate pi. Okay, yes, which, delicious. He was the first person to say it was the ratio of circumference to diameter in like written down. I mean, maybe somebody did it, but they didn't write it down. And it's very important to write things down. Let's see. Oh, he figured out how to calculate, this is the guy you should blame. When you can't remember the surface area of a sphere or the volume of a sphere, yeah, he came up with all that. That's what he did with pi. And he also figured out buoyant force. He invented the screw.
Wow.
Yeah. And an inclined rotating coiled tube is what he called it. But in Greek, because I don't speak Greek.
She's like Wikipedia, I selfish tab.
Oh, he invented the catapult.
What are you reading? Is this Wikipedia on your phone?
Basically, yeah. I copy and pasted it into the notes.
I thought the catapult.
Did he like dunk himself in the best one though?
The best.
Wait, what?
seed.
Dumped himself in Mercury.
Didn't he like dunk himself in Mercury?
I heard some dumb
That's
stuff.
That's what he's getting at.
You're more than welcome to do your final project on Archimedes.
Yes.
Yes, he used catapults to fire rocks at the Romans and defended the city of Syracuse from the Romans. So anyway, let's talk about stuff that floats now that you guys have already done stuff that floats and are thoroughly upset about it. Okay. So, ignoring the weight on the, so let's draw ourselves a little force diagram. Okay? So, what's going on this block that's in fluid? So, yeah.
Rho VG.
Well, no, it's a block. So what's the pressure on the top? Are you sure it's the same as the pressure on the bottom? What do you know about the pressure on the bottom?
It's going to be more than the pressure.
It's deeper, right? It's deeper in the fluid. And we know the farther you are below the surface of the fluid, the more pressure that you have. Okay? Calm down. So, less pressure, more pressure. There's also weight going down, right? But if we're just talking about the forces coming from being in a fluid, okay, how do we figure that out? Well, this is not the full derivation because it's messier. There's an integral, but this is like a pretty good derivation. It works for a cube. It works for things that are similar to cubes. If you have a sphere, you have to do an integral. But basically, we're just going to say we're going to calculate the pressure here. We're going to calculate the pressure here, and we're going to figure out the difference between them, okay? So what's the pressure on the top? Let's say this is atmospheric pressure up here. What would you put for pressure on top? P initial plus rho G D, okay? And let's say you want to solve that for force. Well, pressure is force over area, okay? So what do you do to get force back? Multiply through by area. Okay, so force over area times area gives you force. So that means here's your pressure times your area. That's the force on the top. Okay? What's the force on the bottom? Or what's the pressure on the bottom? P naught plus rho G D plus L. Okay? And that means the force on the bottom looks like this. So here's the force on the top. It's your total pressure from the fluid and the atmosphere, okay, times the cross-sectional area of the cube. Okay, so this could be a cylinder, it can be a cube, it doesn't really matter. The force on the bottom is just this pressure times the same area. Okay? So if we want to figure out the net force from just the fluid, right, this force presses which way? Which way do these forces point?
Which force? It should be equally dispersed, right?
Hold on, so this is the fluid on the top of the thing. Where is it? Where is it pressing? It's pressing down. What about the fluid on the bottom?
It should be.
Pushes
Is this
up,
first?
Straight up.
right?
Dog.
This is just the pressure. It's just the contact, right? So the fluid's below it, right? So it pushes up. This fluid is above it, so it pushes down.
Okay.
Okay? So you have a net force. You add those two forces together. So one of them points up, one of them points down, so you're subtracting these two forces. What do you get? Well, let's write it out. Not zero.
Buoyancy force.
Well, yes.
Yes.
I'm looking for something a little bit more specific.
You get PG.
And it does say buoyancy on the top.
Right.
So we want F net, which, spoiler alert, is buoyant force. So we'll call it FB for buoyant.
Right.
That's going to be the force
On the bottom.
on the bottom, which presses up, minus the top. So F top minus F bottom. And just in case you don't remember Physics 190,
You add if you go bottom minus top or no?
it depends on your coordinate system.
Okay.
Yeah. But, okay, so, well, I guess like this. Okay, so F top, F bottom. Okay, so we said that F top, that's going to be P naught plus rho G D times A. Okay, minus P naught plus rho G D plus L times A. All right.
So P naught and rho GD cancel.
A
So
times PG.
this term cancels, right? And then your rho GD term cancels. So you end up with rho GL times A. Now remember, this is
Three-dimensional. So
a
L is
cube. This is A, and this is L. So if you multiply L times A, what do you get?
volume.
Volume. Okay? Rho G volume. Okay? So the buoyant force on anything in a fluid is rho G volume. Now we derived this for some specific shapes, but it turns out if you go through the longer derivation, this is true for all shapes. Okay? And that's why it's important to leave it as volume. So rho times G, so this is just the density. And this is the density of what? Water? Water. Or of whatever fluid you're in. Okay? And how do we know that? Well, from this derivation, right? We were calculating the pressure from the fluid. So this density is the density of the fluid. Okay? So it doesn't matter if this block or this object that's in the fluid is styrofoam, or if it's a rock, or if it's aluminum, or if it's steel. Your buoyant force does not depend on what your material is that's submerged in the fluid. Okay? It only depends on the fluid. And now you're going to say, well, how do we know if it's going to float or sink? Well, what other forces are acting on it?
Gravity.
Gravity, right? So your whether you float or sink, that depends on your material, not because your buoyant force depends on your material, okay? It depends on the balance between this force and your weight, all right? So if your buoyant force, and which way does the buoyant force point? Up. If your buoyant force is larger than your weight, then you go up, right? You float. If your buoyant force is less than your weight, then you sink, okay? But the buoyant force itself is just a feature of the fact that if you're in a fluid, the top of the object is experiencing less force than the bottom, okay? And because the fluid has more pressure at the bottom, it pushes things up, okay? Because all fluids have more pressure as you go down. Doesn't matter if it's air or water or liquid mercury, which you shouldn't drink, or helium or anything. Okay, any liquid or gas is considered a fluid. So anything in a fluid has a pressure differential from top to bottom. And that's what buoyant force is. Yes.
So if you had a large enough cylinder of, say, water, you could take a cube of any density and drop it in, and eventually it's going to stop. Because the buoyant force will overcome gravity.
In most cases, yes. I mean, if it's not,
Okay,
not like a black hole or
if you
something.
make like a cube out of like unobtainium, something ridiculous, right? But like,
Unobtainium. Except for Futurama.
Uh,
Okay. So yes, I mean, yeah. As you go deeper, you might. Well, let's see. No, it's a linear differential, right? Like, look. If you go deeper in this fluid, does this depend on the depth?
No, it depends on the volume.
No, it depends on the length of your cylinder. Because look, the gauge pressure is linear. So if you're at the top of the water or at the bottom of the pool, the pressure difference is still the same.
but
Yeah.
the buoyant force doesn't change.
Yeah, the buoyant force should be the same because as long as the shape of your object doesn't change, right? As long as the volume of your object doesn't change, actually. The shape can change. As long as the volume of the object doesn't change, it should be the same buoyant force. Yeah. So, yeah, and you can't, since you can't change like mass, right? It's always going to be fairly
So it either sinks or it floats.
right,
Yeah.
right, and it'll just keep sinking.
Yeah.
Yeah.
Otherwise, over time, like things like the Titanic would just magically rise up from the bottom of the ocean because
Well,
the
I'm not
rust,
saying, like-
the rust is limited its mass, so it rises.
It is, yeah. The buoyant force is dependent on your volume. The volume, the fluid, and gravity. Now, I mean, I guess if you get deep enough, you might have a slightly different G.
Okay, yeah, but that's...
And the other thing is about water. I mean, some fluids, as you go deeper. So what you might be thinking of as you go deeper for some fluids, because the pressure increases.
That's what I'm
the
thinking, that
density
the density
changes.
is changing,
Yeah,
but
but it's
that's not what we're talking about.
that has to be over a pretty large scale, unless you're in in a gas that might be more of an issue.
They're down in the gas.
I'm actually really enjoying these questions. They're like a lot smarter than the ones I had to answer yesterday. So, okay.
What was that?
No, it's a department meeting. I'm just kidding. All right. So remember, the density in your buoyant force is the density of what?
The liquid.
The fluid, yeah, the fluid you're in. It is not the density of your object, okay? I'm going to say that one more time. The density in buoyant force is the density of the fluid you are submerged in, not the density of the object, okay? Because every year someone messes that up. Okay. So, if you're underwater, okay, how much, if you're in a liquid or a fluid, how much fluid have you displaced? What volume? Your volume, okay? Yes.
That changes though, doesn't it? Because like that's how they measure fat, for example. That when you sit in the water and you displace so much water.
Okay, we're getting there.
Okay.
So, yeah, don't worry. We'll go.
Right, 'cause there's
You're
like a
on the right track,
mass
but
displacement.
just from a practical perspective, if you put a 1 meter cubed into completely submerged,
Right.
it displaces 1 meter cubed of water.
Sure.
Okay, so that volumes are the same. Okay, yeah, that's so we can agree. And so this is our buoyant force. So this is our buoyant force, and of course, this is the volume of the object that's submerged. Okay, it's the total volume submerged. Okay, what you're thinking of is the buoyant force of an object is equal to the weight of the fluid displaced.
Got it.
Okay, now why is that?
Conservation of mass.
Because you displace that amount of volume of that liquid,
Well, what are you displacing?
the volume of the liquid.
You're displacing the liquid. Okay, so if you're completely submerged, right? That is at the let's see, how do I put this? Okay, well let's just stick with that for now. The buoyant force on an object is equal to the weight of the fluid displaced. Okay. Volume submerged is equal to volume displaced. But we're getting to this point where we're talking about things that are going to float. Okay. So the weight of the fluid displaced and the volume of this fluid displaced are going to be two different things. All right? Okay. So here's let's get to that more. I want you guys to sort of figure it out. Okay, so we're mostly thinking C. Please discuss. We'll vote again. Yay! 2 people didn't answer, but everybody else got it right. So they experience the same force. Why?
Because the fluid is dependent on the fluid.
They have the same volume displaced. Now, that's because the fluid is the same and the volume is the same. So you have the same density, the same volume, and G is obviously the same. What's the wood going to do usually, though? Float. Okay, so let's talk about what that means. Floating. All right? Because when we're talking about the buoyant force, we're talking about this force that points up. But of course, if you're on Earth in a fluid, there's also a force that points down. We call that weight, okay? And it's mg. All right. So how do we decide if we're going to float or sink?
If the buoyant force is greater than.
And let's say this is rho of the object. Okay, it's not air. It's not this thing up here. So this is rho of the object. This is rho of the fluid. So density of object, density of fluid, density of object, density of fluid. If the density of the fluid is greater than the density of the object, what do you expect to happen? You float. Okay? So, did it animate floating? Yeah, it's floating. Okay. I don't know. I just wanted to tell that if something happened. Okay. If you have the other situation where the density of the fluid is less than the density of the object, what do you expect to happen? Sinks. Yeah, this is a nice slides, right? Okay, so for floating objects, right, we can say we can have a force balance equation, okay? Because if the object's floating, what do we know about the force up versus the force down? They should be equal. Okay? So how would you write that out? I need more space. Get rid of our barometer. So let's say we have this block and it's in a fluid. Okay, so this is rho fluid and this is rho object. Okay, what are the forces?
At the surface, mg.
So mg pointing down and buoyant force pointing up. We know if this thing's not moving, this plus this equals 0. Okay? Yes?
But if they're equal, couldn't the block just be anywhere in the water and it just wouldn't move?
Yeah, wouldn't that just be neutral?
And it would only flow if the buoyancy was greater than.
Wait, okay, say that again. I got distracted by
if the net force is 0, then the block can be anywhere in the water.
So he's
But
saying
it's
you
only
put it
if
in
the
the
buoyant
middle
force
of
is
the
greater than the weight that it'll float to the top.
Well, if there's a net force, then what's going to happen?
It will keep going up.
It can accelerate, right?
Yes, but I'm saying if there's no net force, then it can be anywhere in the water.
So this is the tricky part. How do we calculate the buoyant force? What volume?
Of the displacement.
The volume displaced. So it's not the volume of the block.
Okay.
Okay? So if you submerge the block further, what happens to the buoyant force?
Increases.
Good increase.
It gets bigger, which means it can accelerate upward until it reaches
Equilibrium.
equilibrium. Yeah. So the key with the buoyant force is, remember, this is the density of the fluid, not the object. This is the volume displaced. Sorry, that's a terrible writing of displaced. You get the idea.
Yeah,
Okay.
You're right.
So we know that the buoyant force should be equal to mg. Okay, yes.
Just kind of piggybacking off what he said. So then what does it mean to be neutrally buoyant?
What?
Because
I don't know. What does it mean to
Because,
be
like,
neutrally buoyant?
So I had to build UAVs for underwater video camera stuff a couple years ago.
What is a UAV? Okay, what's a UAV?
It's a submersible vehicle. So
Okay.
like, you can shove it under water and it'll stay down there.
Okay.
And you can like take pictures and stuff. But when we designed them, they all had to be neutrally buoyant. And so what we did was essentially this, right? The volume of the actual craft, took that weight and then made the object, the craft's weight, the same as that. So that it wasn't trying to float or sink the whole time. It just kind of stayed there.
Right. So once you're submerged, right, you can get things to stay wherever you are unless you perturb them and give them it's like being weightless, right? You'll just sit there unless someone gives you a tap and then you move at a constant speed.
Okay.
So what you're looking for is you want the weight and the buoyant force to be equal for something that's underwater.
Got it.
But remember, this thing's going to float because of its relative density to the fluid.
Got it. I understand.
So it's still buoyant. Everything has a buoyant force, right? Even when you're underwater, you have a buoyant force, but it changes depending on how far you're submerged in the water because the volume that goes into the buoyant force equation is the volume that's under the fluid. So if your head's out of the fluid, that's not considered part of the volume. Okay. Yeah.
Is he, I don't know, probably I got wrong. What he's saying, the density of the fluid equals the density of the object, something different happens?
No, he's just saying they're designing objects so that when they're completely submerged, the buoyant force equals the weight.
Okay, then
Okay.
What happens when the density of the fluid equals the density of the object?
Yeah, same thing.
Usually
You said something.
that. The buoyant force equals the weight.
Yeah, but we do
So
Always.
they don't sink, they don't float,
They just hang out in the water or fluid. Okay, going back to where we were. So the buoyant force is rho of the fluid, G, and volume displaced. Okay, and then mg. What's another way to write m? Let's write it in terms of density.
Rho v.
Rho v. Okay, rho is of the object. This is the volume of the entire object, so total. And then this is g. Okay, what do we notice is on both sides?
There's a G, so they cancel.
Okay, so now you get this nice ratio. So density of the fluid over density of the object is equal to v total over, I think this is backwards from where I want it. All right. But it works both ways, just this is cleaner. So, okay, like that. Okay? So, what is this, why is this useful? What is it going to tell us? Did I do that right? Yeah.
Well, if you have the ratio of the densities, then you could easily find one of the volumes if you were missing one.
Yeah. Well, what's this ratio tell us? Volume displaced over volume total. What units would that be in?
No units.
No units. So what does it tell you?
It's just a ratio.
A ratio of what?
Of the total volume that's inside of that's submerged.
Yeah, how much is submerged, right? If you have the volume displaced divided by the total volume, that's the percentage of your object that's underwater. And so what this tells us is just knowing the relative densities, we know how much of the object is going to be underwater. Okay? So if you know that you're 50% submerged, okay, that means you know that one of these densities is half the other one. Okay? All right. So here's a second statement. The weight of the fluid displaced equals the weight of the object. Okay? That's a little bit more subtle. Because if we go back to here, fluid times volume displaced times g. That is the weight of the fluid displaced equals mg, the weight of the object. Okay? It's pretty simple. It's just force balance, but it has some implications. That means if you jump in a bathtub, so let's say you fill your bathtub perfectly full, okay, and you drop something in it that floats. Okay, what's something good that floats? Like
A rubber duck.
drop a rubber duck
Right.
into the bath, okay? And the bath overflows a little bit. If you collect all the water that overflows, it will give you the weight of the rubber duck, okay? What happens if you push the rubber duck all the way underwater? Then
They
what's
drown.
that?
It's the force. You do with the size of that?
Then
There's
what
more
does-
water, so there's more water.
So when something's floating, it displaces its weight in water. When something's submerged, it displaces its volume. Okay? So there's a difference when things are floating and when they're submerged. When you think of the fluid displaced by things. Okay? Okay.
Will you repeat that statement? That was like really important. Something displaces something submerged.
Something displaces.
So when an object is floating, the fluid displaced is equal to its weight.
Oh, hell yeah.
When something is submerged, the fluid displaced is equal to its volume.
Oh, baby, thank you. That's what's up.
It's the most excited anyone's ever been about buoyancy. All right. So,
That makes a lot more sense now that loud.
I'm really worried about your life outside this classroom.
I just 3D print stuff. I just make
Oh, okay. Well, that's pretty exciting. All right. So, this is a fun cartoon, but what happens if ice sinks?
You would do that. I can't.
Well, so most things in their solid state sink, right? Because usually, as you go through different states, right, gas is less dense than liquid, which is less dense than the solid. Okay? So the solid state of things usually sinks in the liquid state of things. All right? We know that water doesn't do that, mostly because we've all had a cocktail, or ice water. But what happens specifically to this fish
It does. It's fine.
if the ice sinks?
It'll get cold.
It would get cold, but more importantly, it wouldn't be that worried about how cold it was because it would be dead.
Oh, why'd you do that?
Okay?
How did it
Come on, guys.
Yes.
It's working with PowerPoint here. Okay? It's not like a sophisticated animation tool.
Did that fish have teleportation?
Yes.
What's going on here?
The ice broke up because of global warming. Okay, so ice floats, which is good, because what would happen if ice sank? We'd all be dead. Yeah, we'd never. Yes, everybody dies. Okay, if ice sinks, everybody dies. That's the moral of the story. Okay, and it's a very subtle difference. Okay, here's the density of water, 999.972. Here's the density at 4 degrees, because water does change density slightly as you get colder. Okay, and remember, at room temperature, what's the density of water? Close.
997.
Okay. And here's the density of ice, 999.8 instead of 9. And that's where significant figures come into play, because if nature didn't obey significant figures, we wouldn't exist. So use correct significant figures or be crushed by a giant block of ice. Yes.
Alright, this is kind of silly, but does really colder ice have more density and all that goodness? It's 999, could it be 0.9 if it's even colder?
Yeah, like those ice in Kelvin.
I don't know.
That would really make sense.
I don't know.
Absolutely.
That's a good question. Okay, I have no idea.
Or is ice ice?
It's a good question, though. Sounds like dry ice is carbon dioxide.
Yeah, that's
And it sublimes at atmospheric pressure. It's really fun to play with, too.
Is it like it with the glaze
Okay.
for the drinks?
Okay, here is your chance to do a
Pretty
problem.
cool. That.
Don't blare your cocktail.
It's, yeah.
Okay, so in this problem, we're going to have to use a ratio of densities. But first, let's think about what the problem's actually asking. So if we have an iceberg and it's floating in water, okay, let's draw out the iceberg. Here's the water. So here's the water. Alright, and we'll make the iceberg gray, I guess. So here's our iceberg and here's our water. We're looking for the total volume of the iceberg, right? So we have this ratio that says density of the object divided by density of the fluid is equal to the volume submerged divided by the total volume. Okay, so if we want to look at this, first we have to determine what's the object. So the object, this is going to be the density of the iceberg, right? So this is object. And the amount submerged, that's going to be this. So this is the volume submerged. But what are we asking for? Well, when in the problem, we want to know how much floats. So we're actually looking for this. So just to remember later, when we get our actual answer, we're going to have to subtract it from 100. So 100% minus V submerged over V total is going to give us what we actually want, which is the volume above the water. Okay, so with that we can get started. We know that V submerged over V total is the percentage of the iceberg that is below the surface. So that's this thing. Okay, so now we can actually plug in our densities. That's going to be V submerged, so P object, rho object. Rho object is going to be 917 kilograms per meter cubed. Rho of the fluid, that's going to be the seawater, is 1,030 kilograms per meter cubed. So when we divide these, we get about 89%. But remember, we know we're not done because this is the iceberg below the surface. But above the surface, that's 100% minus 89%, which should give us 11%. So the total amount of iceberg above the surface is actually 11% because that's this. All right.
Yeah, true. Well, it depends because
Oh no. Okay. All right. This needs some discussion. Take a minute and a half.
They're still flipping. Oh, jeez.
It's better.
Still discrepancy.
Yeah.
Who's the 10%?
Okay. What did we learn about density? Literally 5 seconds ago, or well, 2.5 minutes ago.
It's a ratio.
yeah, it's a ratio,
That's
The
right.
ratio of density tells you how much the object should be submerged.
Oh.
Okay? As this ratio gets closer to 1, should more or less of the object be submerged? More. Okay? So the more you're submerged, the larger your density is relative to the fluid you're in. Okay, so which one is the most submerged? A. Which one is the second most submerged? C. And the least submerged is B. So it should go A, C, B. Which gives you answer C. That's a lot of letters, but you get the idea. Okay? Okay. Here is this is going to be a very hard problem because you guys had trouble with this one. But here's a much harder problem.
Great.
I'm going to give you 2 minutes because there's a lot of reading. This is quiet time. So 2 minutes of quiet time. I'm going to eat this candy.
Oh, you guys.
All right? So we've got some discussion to do. Please discuss, and we will vote again. Oh, yes! All right! Yay! This is amazing. So if the object is completely submerged,
This one didn't even answer.
well, okay.
It doesn't count.
If the object is completely submerged, the volume displaced is equal to the volume of the object.
Yes.
Okay? Since we know styrofoam is less dense than water, if they have the same density, the water should weigh more. Okay? All right. Stop.
Hey, here we
Vote,
go.
vote. I can delete questions. Okay. Next question. All right. Please discuss. We'll vote again. Is it always the same person?
Yeah.
Yes, better. Well, it could be better. It could be better. Yes. So remember, this is a block of wood that's floating. There's no water displaced. When you put the block of metal on top of the wood, it displaces some water. Because this is floating, even though it's metal, it displaces its weight, which means the weight of the metal and the weight of the water should be the same. Yes?
So if whatever object is placed and it doesn't displace water, you can assume that it's just weightless, like it's negligible. You don't have to.
Well, it depends on if it's at the brim. But
Like in this situation.
Yeah.
Yeah, so you
Yeah.
wouldn't have to worry about it when it sinks.
yeah. But if it sinks at all, it's going to displace water.
It's sink, the block would sink because the block is.
Yeah, this thing's going to go down.
That's what I'm
It's
saying.
going to displace water.
That's what I'm saying.
Yeah, this is how boats work, right? Like
Yeah.
boats are obviously more dense than water, especially when, well, not always, but when they're made of metal, that's more dense than water, but they still float. This is how boats work. Okay. Do you guys want another one?
Heck yeah. Hell yeah.
Okay.
Oh.
Please discuss.
That's D.
Okay. All right.
All right.
Well, the answer is C
Tell
because
you.
when it's floating, what does it displace?
Itself. Water.
Itself. It displaces the amount of water that it is, right? Because once it melts, it changes density, takes up less space.
Yes.
All right.